Hello, welcome to the webinar today. Just going to give it a few minutes before we get things started. Well, hello all for you still joining. Just going to give it a few minutes before we get started today. I'm Sam from the Energy Management Association. I'll be your moderator today. So while we wait, why don't we start things off with a quick poll so we can learn a bit more about your background. So tell us, what industry sector do you work in? I'll give it a few more minutes. For those of you just joining, we're starting things off with a quick poll on your background. Okay. Looks like a big chunk of you are in commercial and healthcare and other. I'm interested in what that other is. You can put that in the chat. I'd like to know where you guys work. Okay, well, we're 2 minutes past, so why don't we start hopping into things. Before we get started, I do have a few housekeeping notes. I encourage you to submit questions at any time using the Q&A section. The speaker will address, two speakers will address any questions at the end of the webinar, time permitting. And in terms of continuing education credit, you will receive an email within 1 week with your proof of attendance. Today's webinar, and thank you again for joining us, is First Steps for Improving Air-Cooled and Water-Cooled Chiller Performance and Energy Efficiency. It's brought to you by the Energy Management Association and its corporate member, ETC Group. A little bit about EMA and where I work. We are dedicated to providing education, training, and certification to energy management professionals for the benefit of the building owner. Our energy management professional certification features commissioning-based curriculum that maximizes energy efficiency and optimization for building systems. And of course, our member ETC Group is a leading energy efficiency engineering firm with over 33 years of experience. They reduce building energy waste, cut operational costs, and create healthy and comfortable environments to patients and tenants. So I'd like to introduce our first expert speaker today, Jim Crockett. He has over 25 years of experience in the HVAC industry in general, and also 15 years specializing in energy efficiency. Jim has been the lead engineer on HVAC recommissioning projects at ETC Group around the world and has provided technical guidance in support of ETC Group's monitoring-based commissioning program. So without stealing any more time today, I'm going to hand it off to Jim, our first speaker, so we can dive into things.
Thank you, Sam. So it's a pleasure to be here today. I'll be talking about air-cooled chillers. Greg Jimmy after me will be speaking about water-cooled chillers. So now, my focus is going to be on how to save energy using air-cooled chillers. And in order to understand that, and also in order to understand Greg's presentation on how to save energy with water-cooled chillers, I want to start by reviewing briefly reviewing the refrigeration cycle. Some of the changes that we're going to propose or that we're going to make are dependent on an understanding of how the refrigeration cycle works. So we'll start with that. In understanding when we think about the refrigeration cycle, it's helpful to, I've found that a pressure enthalpy diagram can also be helpful, or often be helpful. The way this diagram works, for those of you not familiar with it, is as you move from left to right on the screen, you have a, as you move from left to right on the screen, you increase energy. So as you move from left to right, you absorb energy from the surrounding areas. Or the refrigerant absorbs energy. As it moves from right to left, it releases energy. As it moves from bottom to top, the pressure increases. And when you go from top to bottom, the pressure decreases. Now I'll very briefly walk through one iteration of the refrigeration cycle with an air-cooled chiller. In this particular air-cooled chiller has an economizer cycle on it. So with the cycle, you can really begin it anywhere you want. I'm going to begin at the evaporator. So the evaporator, if we look at our pH diagram, or as we move from left in the evaporator, warm liquid from the building delivers heat to the refrigeration or to the refrigerant, and it absorbs heat from that. The pressure in the evaporator stays constant, and so it moves from left to right on the pH diagram. From there, the warm evaporated refrigerant goes over to the compressor, where it is compressed. And I apologize in advance. Engineers are just not good at naming things. A compressor compressors, a condenser condenses, an evaporator evaporates, etc. So in the compressor, we compress the refrigerant, going from a low pressure to a high pressure, and in the process, we also add some energy to the fluid, which is why it moves from left to right. You'll also notice that we are at this point where we would call outside of the dome. The dome is this border, the border that traced on the pressure enthalpy diagram. Inside the border, the refrigerant is a mixture of vapor and liquid. Once it's to the right of it, it's called superheated, meaning it is now warmer than needed to fully boil. And when it's to the left, it is subcooled, meaning it is fully liquid. Okay, so compressor is the next step. Okay, and just in the interest of being thorough, we briefly remove some oil from it. And onto the condenser. So the condenser is on the high pressure side of the system. We're receiving hot pressurized vapor from the compressor. And in the condenser, we move from right to left on the diagram, and our refrigerant condenses. It goes from vapor down to a liquid. And in fact, in a condenser, we will generally have some degree of subcooling. In other words, after we've fully cooled it into a liquid, we'll continue blowing air across the condenser and continue cooling it. In this particular case, we have an economizer as part of the system. So we have liquid coming off of the condenser. We take a small part of that and flash it. In other words, we cause it to evaporate, which makes it absorb heat from the surrounding areas, or from the economizer in which it is. We take the balance of the refrigerant and run it through that economizer. So we pre-flash, we sacrifice some of our refrigerant to cool the rest of it down. And what that does, if we look at our P&H diagram, is it slides us further to the left. It slides us further into subcooling. The reason we do that is because we don't want any of the liquid to accidentally evaporate before it hits the evaporator. So there's a small subcooler there. The medium pressure vapor that we flashed for the economizer goes back to the goes back to the compressor, and the subcooled refrigerant makes its way back to the evaporator, and that's where the cycle ends. For most of the rest of my brief remarks here, I'm going to be talking about I'll be focusing largely on the compressor because that's where most of the energy is. By the way, if you want some additional information on how a refrigeration cycle works, I covered it in 5 minutes. There's at least 1 or 2 PhDs worth of information on refrigeration. So here's some basic links. If you go to Google or YouTube and just say, how does a refrigeration cycle work? You'll get more information. But that's a very quick overview. So a chiller takes advantage of the refrigeration cycle. You've got the high side, which includes the condenser, and the low side, which is the evaporator. And so in a chiller, the evaporator absorbs heat from the building, and the condenser of an air-cooled chiller anyway takes that heat and rejects it out to atmosphere. When Greg talks to us with the water-cooled system, you actually have a water-cooled condenser instead of air-cooled. The compressor increase. Let me start with the evaporator. So the evaporator is the low pressure side of the system. The compressor raises the pressure up to high pressure for the condenser, and it remains at high pressure until it goes through the expansion valve. We'll come back to all of this in just a minute. We're still doing an overview, but the reason we're going to focus on the compressor is because nearly all of the energy used by a chiller is used by the compressor, and they use a lot of power. When you walk into a building, you'll be in a 200,000 square foot office building. When you walk into the chiller plant and look at the chiller compressor, probably 25 or 30%, depending on weather, of the overall power being used by the building is used by that single piece of equipment. So if we can find a way to reduce the compressor's energy usage by 10%, we're reducing the overall building by 2 or 3%. We're dropping our power bill by 2 or 3%. And 10%, I think Greg's going to show us an example of one that was even higher than that, but 10% is a realistic number. So how do we reduce the amount of work done by that compressor? Well, again, the work that the compressor is doing is it's taking refrigerant at a low pressure and raising it to a high pressure. So there's really only from a very high level, there's only a couple of ways to reduce compressor work. One of them is to reduce the amount by which we're increasing the pressure. And the second way is to decrease the amount of refrigerant being pressurized. So there's a couple of ways of decreasing the compressor work. So the pressure required to go from low pressure to high pressure, you'll hear the term lift used in the industry. And lift is basically the distance between the low pressure and the high pressure sides of the system. So one way is to decrease lift, and we can do that either by raising the low side or decreasing the high side. And I'll talk briefly about both of those. So the first one is raising the evaporator pressure or raising the low side. If the inlet side of the compressor isn't quite as at a low of a pressure, you don't have to do as much work to get to the condenser pressure. And so the most common way of affecting this is by increasing your chilled water supply temperature. If your building can get away with 50-degree water instead of 42-degree water, you can save quite a bit of energy. And what you're doing when you raise the chilled water supply temperatures, you're making the refrigerant cycle not have to run as cold. You raise the lower end of your pressure, or you raise your lower pressure. And each degree Fahrenheit that you raise an air-cooled chiller, translates into about 1.5% energy savings. So if you were able somehow to go from 42 degrees Fahrenheit of chilled water supply to 52, you could expect around 14 or 15% energy savings at the compressor. So that's the first way to do it, but it's not the only way. Another way is to improve your approach. So when the system is running well, the temperature of the chilled water leaving the chiller is within a degree of the evaporator temperature. So your cooling cycle has your refrigerant down at 42 degrees. You should be getting 43 degrees out of your chilled water system. But what if something happens to compromise the approach? If something causes the approach to deteriorate, let's say instead of a 1 degree approach, by the way, approach is the difference between refrigerant and supply. I think I might have said that. If somehow approach were 5 degrees instead of 1 degree, if you want 43 degree chilled water, you need to take your refrigerant down to 38 instead of down to 42. You have to do a substantial amount of additional work. Your compressor has to work quite a bit harder. So there's a couple of things that can cause your approach to deteriorate. One of them is fouling in the refrigerant tube. So that's just essentially, think of it as gunk or buildup happening on the inside of the heat exchanger or the heat exchanger barrel of your chiller. The second thing that can happen is if your system is low on refrigerant. If your system is low on refrigerant, there's less mass flowing, and so it has to be, to get the same amount of cooling, it has to flow at a colder temperature. So two things that you can do if your system is low on refrigerant, add refrigerant. This is an issue in a surprising number of chillers. Look at your chillers. A lot of times on your chiller display panel, it will tell you what the refrigerant temperature is. Compare that to the chilled water temperature. If there's a large delta between those two by more than a degree or two, something's not right with your system. You may need to add some refrigerant. You may need to clean the chiller tubes, but something is not right. Let's see. Let me move to the next one. Okay, so as I was saying, you can either clean the evaporator tubes or add refrigerant. It's also worth pointing out that if you don't have an approach problem, you're not going to save much energy by doing extra cleaning to the tubes. Once you're within a degree, that's about as good as it's going to get. Some companies do it, clean their evaporator tubes as a matter of annual maintenance, which I think is a good idea to make sure that they always keep their approach where it needs to be. Be sure to check your refrigerant. So now we've talked about raising the evaporator side of the equation. Is there anything we can do to drop the temperature of the high side, the pressure and the temperature of the high side? So one thing that we found is that the condenser temperature of most air-cooled chillers comes from the factory set for about 115 degrees. And 115 degrees it's hot enough to reject heat to atmosphere. You've just absorbed a bunch of energy from the building, and you've got to increase the heat of this energy high enough that it can be carried away by atmosphere. So if you're in Phoenix and it's a 115 degree day, 115 degrees in your condenser is not going to allow you to transfer any heat out. So even if it's set for 115, what happens is, whoops, something happened. Okay, so even if what will happen at 150, if the refrigerant in the condenser is not hot enough to be for the energy to be carried away to atmosphere, the fans back down and the condenser gets hotter. The condenser will automatically get hot enough to carry the heat away. Now, what that means is that you'd be able to get away with setting it lower. If you could set it for 95 instead of 115, most days that would still be hot enough to be able to reject your heat to atmosphere. And if you did have a 105 degree day, the condenser temperature and pressure would automatically rise in response. So that's one way to lower your condenser pressure, is to is to lower the condenser pressure set point. So we found that most technicians don't know how to do that. It's you have to modify the onboard controller or change a setting on the onboard controller. So you may have to do some digging into this, talking to the right folks to find out how do I set my set point lower. This is especially effective in cooler climates. We were working on a project in England, and England just doesn't get as hot as, you know, some parts of the US. Most of the year is spent at cooler temperatures, and this was a manufacturing type environment. And so they needed year-round cooling, and they kept their condenser running at 115. You know, they rarely got above 80 degrees, period. So they were running much too high of a condenser temperature. So in locations like that, this type of adjustment can be especially helpful. We need to be careful to not reduce the pressure too far, because if we do, we won't have enough pressure to eventually overcome the pressure reducing valve or the expansion valve. Another thing that we can do to lower the condenser pressure is to use a bigger condenser. If you have a bigger condenser, then the refrigerant doesn't need to be as hot in order for it to reject all its heat to atmosphere, because you've got more surface area. Unfortunately, upsizing the condenser isn't usually an option. However, you can more effectively use the condenser space that you have. If you were to look at most condenser coils with a thermal imaging camera, you would find that part of your coil is too hot. It's being used for what they call de-superheating the refrigerant. De-superheating has to happen. I mean, you've got to cool the refrigerant off before it'll start to condense. But, you know, you hate to use the first third or fourth of your condenser for de-superheating. And then you've got, a lot of times with your thermal imaging camera, you may find that you're collecting liquid refrigerant down at the bottom. And so essentially you're only left with, you know, 50 or 60% of your overall condenser area available for condensing. So how do we fix that? Well, one way, you can use what they call a de-superheater. It's similar to the economizer that I described earlier, where you peel off a small amount of liquid refrigerant and cause it to flash. That allows you to pre-cool your refrigerant on its way into the condenser, so that the refrigerant is cooler, and so that you can actually use more of the area for condensing. You do pay a small penalty in capacity there. Some of your capacity gets used for, just as the economizer does. Some of your refrigerant gets used to pre-cool the refrigerant. However, if it allows your compressor to only need to maintain a 95 rather than a 105 degree temperature, it's probably a good sacrifice to make. Another thing that you can do is collect less refrigerant at the bottom of your coil, and you can add a receiver down at the bottom. You know, space permitting, you can add a receiver down at the bottom in which the refrigerant can collect. It's important to make sure that it is fully liquid by the time it leaves, but it's a lot more practical usually to add a receiver down at the bottom than it is to try to expand the size of your coil. And by doing that, you essentially increase the area available for condensing. So by doing this, you can substantially reduce the amount of energy available for condensing, which allows you to run at a lower temperature and pressure. Speaking of temperature and pressure, the way most fans are sequenced on an air-cooled chiller is they come on one by one. And here, you know, I'm using red to indicate 4 fans running at 100%. And that's typically how they run. And then if we need more capacity, we'll turn on the next 2 fans, the next 2 followed by the next 2. And there's 2 issues with that. One of them is, if you're familiar with the fan affinity laws, it takes a lot more energy to run a fan at 100% than it does at 50%, across the same path. In fact, it takes about 8 times as much energy to run at 100% than it does at 50%. The second problem, which was less obvious to me, is that, well, you're only blowing air across, in this case, 40% of the coil. And so only 40% of your coil is being used for, powered heat transfer. If instead you can program your condenser to have all of the fans move in parallel, you win twice. Number one, your fan energy goes down thanks to the affinity laws. And second, your heat transfer at your condenser becomes much better, which means you can lower your temperature and you can lower your pressure. And this will generally require some sort of either a modification or an aftermarket type of controller, but it can result in substantial compressor savings. I'm almost finished wrapping up, but in doing this, I'm making it sound like you want to take your high side pressure as low as you can get it, and you do, but you need to be careful, because otherwise you're not going to have enough pressure to push refrigerant through your expansion valve, and at which point no cooling happens. The other thing that could happen is if you bring your two pressures too close together, most chillers have a minimum lift that is required. And so you don't want to go lower than that, or the compressor doesn't know what to do. Now, addressing the expansion valve, you can go with an electronic expansion valve. That has less resistance, which may buy you some room. But one other consideration, one other thing you can do is you can add a liquid pump. Once the liquid has condensed, and it's borderline, if it's just barely outside of the dome and you're worried that it's going to warm up and start to flash on its way to the evaporator, you can add a liquid pump. It is much more, just from an efficiency standpoint, it's much more efficient to use a pump to pump a liquid than it is to use a compressor to squeeze a gas. You're looking at like 70 or 80% efficient rather than 30% efficient. So if you can run your condenser a little colder, that allows your compressor to not work as hard, and it transfers potentially some of that work to a liquid pump where it does it more effectively, and that gives you enough push to get through the expansion valve. Not all systems lend themselves to this. This is dependent on the type of refrigeration that you have in your system. It's not an off-the-shelf solution. Some chillers just aren't good candidates. If you've got like a flooded type system, it may not be a good candidate. So these are good things to think about. Don't go out and buy a receiver and put it on your air-cooled chiller and expect to see savings. This is an engineered solution. It's not just an off-the-shelf thing that you can do. But to recap, compressor savings result from reducing lift, bringing the high side and low side pressure closer together. Most air-cooled condenser pressures are by default set for hot climates. If you're not in a hot climate, look at resetting that, the default. You want to maximize the area in your condenser available for condensation, because that allows you to run at a lower pressure. You can get that by adding a desuperheater to buy some room at the top, add a receiver to buy some room at the bottom, and you've got to keep your pressure high enough for the system to still work. That is all I have. In a minute, you'll hear from Greg Jimmy, who's going to talk about how to save energy with water cooled systems.
Okay, so let me just give a few words on Greg Jimmy, who's an energy engineer and analyst at ETC Group. His main roles are the analysis and identification of energy efficiency opportunities, and he works on a wide range of energy systems, which include campus-wide, whole building, and small subsystems. And his experience also includes whole chiller plant commissioning. So Greg knows his stuff, so I'm going to let him finish out the presentation for us. Greg?
Great, thank you. And thank you, Jim and Sam. EMA, for having us. I'm excited to be here. I'll be diving in a little bit deeper, covering some of the same sort of strategies that Jim had gone over on the air-cooled side of things. Water-cooled, air-cooled chillers, they all use the same refrigeration cycle. So a lot of the same principles are going to apply here. Just the way you go about doing it on a water-cooled system is a little bit different. I've got some real-world kind of data-driven examples that I'll walk through and show you some data and trends that will, exemplify some of how these strategies actually end up improving chiller efficiencies. So we'll start off with what the first most common solution is, getting away with warm chilled water. That's something that isn't new to anybody that's familiar with chiller operations on how to save some energy. But what may be new to them or news is the way in which you want to go about doing it. How do you know when you can reset to warmer water, or how warm can you go? So a couple things that we will be looking at here is to give you a strategy on how to go about automating that process and making your system respond. I like to think of it as ebb and flow, or respond to demand of your systems and the capacity required to satisfy your chilling demands. So here's an example in which we implemented a differential pressure reset as well as a temperature reset. I think one really good way to go about doing this that we've had a lot of success is to see how they interact one another. The differential pressure, typically we would like to respond first to allow the system to get more flow to those coils, and then the temperature has a longer lag time. So that's generally the second leg, or the second step you can go after. The beginning here, this is August in Phoenix. So we implemented a differential pressure reset kind of the first week here or so. Previously, they were running at a fixed set point. The most obvious thing you get away with here is that you'll see we start to reset down to the lower end of the pressure thresholds, even in August. So, we're still seeing 100+ degree days pretty much every day throughout the month in August, yet we're able to back off on pressure, at least half the time, maybe every other day, but for the most time, at night, you're able to back off a little bit. So you'll see some efficiency gains associated with that as well. So, this top line is the chilled water temperature. You can see that we're mostly hanging out around 42 or so degrees until we get later into the month, where we're able to reset up to as much as 45, 46 degrees. And that's really where you see this dip in the efficiency here. This bottom graph here has the red line being the chiller plant efficiency. And we're looking at the chiller plant as a whole. So, the chiller is the largest consumer of the energy, and that's why you're seeing the largest dip, or the largest reduction on that value there. And just to reiterate, a lower kW per ton is better. It's basically less energy consumed to provide the same amount of ton of cooling. So this just gives you that example of really where the rubber hits the road, and saving the energy on the chiller really shows up from increasing that chilled water temperature. Yes, you do get pumping energy savings from the DP, but the largest consumer obviously has a larger impact on the chiller side of things. So then you may be asking, well, what valves do I look at? How do I go about resetting my differential pressure? This is a little bit deeper of a dive on seeing the interaction there. This is, again, at a hospital in Phoenix. So you'll see these valves increasing up to 100% during the peaks of the day, and the differential pressure responding accordingly to satisfy their cooling demand. For what it's worth, this system is controlling to about a 75-degree average valve position. So as they get above 75, that's when you should expect your pressure to increase. And then subsequently, as they back off in the nights and the evenings, that's when the pressure kind of follows suit and backs off as well. So you're achieving that pumping energy savings in all of these areas on the low end at night and in the morning. One thing to note is that the air handlers are not necessarily your most important or end of the line, but those are maybe good indicators. But the real takeaway is that you want air handlers that move up and down, that ebb and that kind of exhibit that profile that your building does as a whole. those are realistically the ones that you want to incorporate into your differential pressure and chilled water resets, because they're going to be acting as a proxy for the overall building needs. Next slide here kind of gives you a little bit more of a visual on how you go about doing that. Generally speaking, like I mentioned, you want to do differential pressure first, as far as responding to the demand first with the pumping, and then secondary with the chilled water. So in this graph, you can see the beginning of we would say a PID loop, or a pressure, control loop of cooling demand is maybe another way to think about it. As the first half of that loop gets to 50%, where 100% is basically your design point, 50% would be somewhere halfway between that. So you drive your differential pressure up from minimum to maximum. So I've got shown out here of maybe going from 15 psi to a 20 psi differential pressure. And then once you get to your maximum pressure, you're going to start then stepping down your chilled water temperature as the cooling demand continues to exist or go up. So that way you're kind of capturing all of your savings on the chiller first, and then or as much as you can, and you're kind of paying a pump penalty. But usually it's worthwhile to pay that pump penalty because of the energy saved on the chiller. Again, chiller compressor energy is by far the largest consumer. So the second component of this is going to be getting into the condensing water side. So a similar here is that we want to bring the top down, or bring the ceiling down of the enthalpy pressure diagram here. So in this example, we are going from maybe 85 degrees to say 60 degrees. A lot of chillers in say Arizona are going to be designed for like an 85 degree entering and a 95 degree leaving condensing water temperature. So a lot of times you'll see chiller plants set up where they're just controlling to that design point. So it only ever controls the condensing water down to 85 degrees. Or maybe you've got a smart designer and they take it a little bit further and they say, hey, we're going to go to 70 or 75, something like that. But I think something that's missed a lot is how much is still left on the table by stopping it at that point. So, realistically, we want to push that down as far as we can. And the same sort of stipulations will apply here, is that there is a limit, and it's generally comes down to a minimum lift requirement that's needed by that compressor. For example, a York chiller, probably think of it in terms of temperature, maybe around 8 degrees between leaving chilled water and leaving condensing water. A train chiller may be looking at it more as far as a pressure is concerned, of maybe, let's say, 4 psi between the two barrel pressures. So you need to have something there to establish some work for that compressor to actually do, and allow also enough pressure to continue the cycle to actually happen. Next slide here kind of gives a visual example of that. So you can see here that we've actually dropped this system down to about a 58 degree condensing temperature. And this, I want to say, is in November in a Phoenix area, same hospital. But you can see that we're hitting that red line, not very often. But when you do get there, that corresponds to the kind of the most efficient points that this chiller plant is exhibiting. And if just to give you kind of the visual to think of, if you were to just say your set point was at 70 degrees, that would be somewhere up in here, and that would effectively sit your best operating point closer, 0.5 kW per ton. So now, because we're driving it down to 58, that's the difference in efficiency gains. So now, instead of staying up closer here to 0.45 or 0.5 kW per ton, now we're talking 0.35 or 0.4 on those same points, or under those same conditions. So whereas you can drive that condensing water lower than I think most people would think. One thing to note here is that when you're doing a design, or if you've already got your chiller plant built out, if you have the opportunity to take advantage of additional cooling towers, basically you have a headered system, you have some redundancies built in place, it's definitely worth considering taking extra towers in. So basically N+1 or N+2 towers to chillers. Same sort of concept is that you're running more tower fans, paying that fan penalty to offset the cost of the energy consumed by the compressor. There's obviously an inflection point where the diminishing returns that trade-off isn't necessarily worthwhile. So I wouldn't say 5 cooling towers to 1 chiller or anything crazy like that. But usually N+1 is a pretty worthwhile trade-off. So that's definitely something worth noting in reprogramming your current system, if piping and whatever permits, or if you're looking at a redesign or a new build, definitely something to consider is those headered systems and to allow to give you that redundancy and additional. It comes down to additional surface area to allow for that heat rejection to occur. So this is kind of like story time I have called out here. So it's not always about set points. It's not always just about resetting your temperature on the chilled water to be warmer or resetting your condensing water to be colder. Those are great places to start, but there's a lot of devil in the details. There's other things that will happen, and a common misconception is that, hey, well, I'm meeting my chilled water temperature set point, so my chiller is good. I get it annually serviced. It's as efficient as it's going to be, but that's not always the case. There's a lot of things that will go unnoticed because you're still meeting that chilled water temperature set point. It could be things like low refrigerant, like Jim had expressed. You can see that kind of in your approach temperatures. You can have too much refrigerant. You can have flow concerns or flow issues where you're overflowing or underflowing the system. That'll impact the ability of the heat transfer to get out of the refrigerant or into the refrigerant, depending on how you want to look at it. If you have maybe too much oil in the system from what it was built, maybe overfilled the oil too much or put it in twice. I know that sounds crazy, but I've seen it. That'll actually impact the heat transfer as well. So now everything's basically coated with oil, and that'll impact the ability of that heat transfer to occur. You can have like a failed O-ring and have rapid refrigerant loss. So there's other failures, other mechanical problems that can happen that you may or may not notice. I would hope that a refrigerant leak is something you notice, but there's other things that are less obvious. So this is an example of one that we had found was actually a mechanical installation, not done quite right. We had been looking at these chillers, their sister or their twin chillers here, and you can see in this top graph is the refrigerant leaving temperature. And this red line is chiller 6, and the blue line is chiller 5. And the same thing applies down here. This is their efficiency over the same time. So, the red line here showing the significantly warmer refrigerant leaving the compressor. We're talking 15 or so degrees there. And then that corresponds to a degraded or worse efficiency on that same chiller. To see 20 to 30% worse on these chillers was something that we were seeing pretty regularly. And we couldn't quite figure out exactly what was going on, but we could see that something was off. So we dove a little deeper. We got in on site. We started to manually manipulate the way these chillers were operating. We first kind of tried to level the playing field. We equalized flow. We did everything in our power that we could to make sure that they were as close to the same capacity or load as one another. And even in doing that, we still were seeing the compressor consume more power on chiller 6. So what happens is that when we started to manually manipulate the way the capacity control works, more modern chillers will use VFDs, inlet guide vanes, and variable geometry diffusers. And those are all ways in which the compressor can modulate up and down as load varies in your system. So without going too detailed into that, we basically manually manipulated how much capacity one of the chillers was able to do. And when we were trying to actually increase its ability to capacity, it was decreasing. So something wasn't quite right. We physically were looking at the way the actuators on those variable geometry diffusers were moving the dampers, or if is a good way to think about it. One of them on chiller 6 was about 90 degrees different from the one on chiller 5 when they were at the same position. So despite that was kind of part of the thing of we were like, that's got to be it. That's the part of the problem. So what we did is we got approval from the facility to shut down this chiller, let us make the repair, reorient the actuator on that shaft, and then fire the chiller back up. And it was pretty amazing because, the same day, the same chiller we saw a 30% change in its energy consumed. Now, after we made the repair and made that change, it was pretty much right in line with its sister or its twin chiller. So, you know, you can see these chillers now pretty much a flat line. They're going from, you know, I just picked this is about a week after the repair had been done, and they, for all intents and purposes, act the same. And this is just great to see, because as one chiller staged off, the next one staged on, you kept that same efficiency profile. Also, the discharge refrigerant temperature now comes much more in line. We're no longer seeing that 100 or 105 degree leaving temperature. So that was just a really cool, clear-cut problem, solution, and then obvious result and savings from fixing that. So I think that's pretty well it as far as the slides that I wanted to go over and cover. I think we've got some questions coming through, and I think Sam is kind of chaperoning those. So we'll get into that next.
Great. Okay, thank you both. And let's dive into the Q&A section. So if you have a question, please feel free to submit one. Start off with the first one. Greg, I believe this one's for you. What is the best way to determine the system ranges for chiller water temperature resets? And then also the same question with DP.
Oh yeah, that's a good one. I actually meant to cover that. So, you know, generally go ahead and leave your bottom where the system was designed. There's a handful of cases in which maybe you used to be manufacturing and now you no longer do manufacturing in that facility, that will give you the room to maybe come off of that. But you know, the bottom is a safe number to say this is where it was designed. You want to still allow the system to get to that design point, because it was engineered at some point or another that said this is where we need to get on the worst case scenario circumstances. The biggest problem there is that a lot of times they just run there all the time. So putting in the reset allows you to back off when you don't necessarily need to be there all the time. So let's just say 42 degrees is probably a safe number to go for the bottom end. I wouldn't necessarily say you really need more than that. Even for mechanical dehumidification needs, there's kind of diminishing returns beyond 42 degrees. Unless you've got some really extreme conditions that you need to maintain in like a clean room or something like that's maybe extenuating circumstances. But like even in hospitals, they have ORs that have pretty tight requirements. 42 degrees really is probably all you need. There may be some old equipment that needs a little bit more, but you know, that's where it's like considering, is it an old valve? Is it an old coil? Getting that replaced to allow you to go to a warmer chilled water is probably worth it. To, you know, just to go from, you know, 40 degrees to 42 degrees, you're talking about 3-4% on your efficiency in that chiller. And that can easily pay for a valve in a lot of cases of, you know, $7,000 to $10,000. That's definitely not unheard of. So that's definitely worth considering. So that's your low end. The high end is kind of where you start paying too much of a pumping penalty. Again, all of these things are kind of finding that happy middle ground. So I would say maybe a more generic answer would be about 50 degrees. I wouldn't say go warmer than 50. At that point, you're really rip and flow through the chillers and the coils. You're probably starting to pay more of a pumping penalty than what you're saving on the chillers at that point. Same sort of question, same sort of answer with the differential pressure. As far as your maximum pressure, again, kind of let it get to what it was designed to do. Just don't let it be there all the time. So if it was designed for 22 PSI, let that be your maximum. As far as the minimum, maybe half that. It really kind of depends on your piping and what the system requirements are. I would say a general rule of thumb would be take your end of the line valve, the last chilled water valve in the system. What's that valve's pressure differential requirement? And then you can measure it at that valve. So say it's a 4 PSI valve. You can go take a pressure reading at that valve, start stepping down your pressure set point, whether that's measured remotely or at the plant. It's kind of, you know, arbitrary, but just some reference point, start stepping that down. And then when your measurement at the end of the line valve is close to 4%, so maybe you want to leave a little extra at 4.5, that would basically correlate to your minimum DP on the reset.
Okay. So Lisa Dacus has a question. So regarding lower, excuse me, here we go. Regarding lower condenser water temperature, can you describe the trade-offs from increasing fan and pump energy versus lower CW temperature? Also, if you have multiple towers, how do you recommend making sure we still meet minimum/recommended flow to prevent scaling in lower load conditions? Either one of you feel free to jump in here.
I'll jump into it, and then if Jim, if you want to add to it, feel free. I'll start off with the minimum flows. The safe answer is to hard code a minimum on your pumps that corresponds to that on the towers. So if you've got 1,000 GPM minimum that those towers require, usually you can reach out to your chiller, or excuse me, your cooling tower manufacturer, and they'll give you the range in which those towers can operate. I believe California has like a 50% turn down requirement. So that's not unheard of. So let's just say that that's kind of going to be the standard if it's not currently in your facility. But 50% turn down on your towers is usually pretty safe. So that would basically mean that you, instead of running one tower at full flow or design flow, you could run two at 50% flow. So that would be without changing your pump speed. One thing to note is that chillers also have a minimum. So you need to be above basically the greater of the two. So if your tower has a lower minimum flow than your chiller does, sorry, your chiller gets to rule the roost in that case. So make sure your chiller is taken care of. Chillers, I would say they typically don't have a full 50% turn down. So definitely check that. That usually can be your limiting factor there. As far as the trade-offs and the increasing the fan energy and the pump energy, it's really just look at your math of what's your kW consumed by your chiller and what's the kW being consumed by those cooling tower fans and pumps. As you decrease that condensing water temperature, you'll obviously see those fan powers ramp up. But you should also see your compressor energy go down. So there's kind of that happy medium of determining, that's why I was saying is don't run 5 towers to one chiller kind of thing. That's more of one of those scenarios of like that trade-off probably isn't there. But to run 2 towers to one chiller, I would say it's probably there, as long as you can maintain your flow requirements. Hopefully that answers your question, Lisa. Jim, was there anything else?
I'll add a little bit. So in terms of finding the trade-off, one thing it's important to remember is that with chillers, as the temperature changes, there's a linear response for chillers. On the pump and fan side, there's an exponential response. So for example, as you increase your tower speed from 50% to 100%, there's an 8-fold roughly increase in power consumption. At the same time, when you go from 50% down to 40%, there's very little, you're already at the flat part of your exponential curve. There's very little additional improvement. And so it ends up so basically there's what we will usually do is pick a spot around 80%. We'll ramp the cooling tower fans up until they're running at 80% speed, and then we will let the chillers, we'll let the temperature rise until it's a cap and release type of approach. So we're trying to avoid running the towers at 100%. By the time you get them down to 80%, you've cut their power in half. I realize I'm giving a somewhat non-definite, squishy answer, but those are the two things to consider. Greg covered the specifics. I wanted to cover the general principle. You're comparing an exponential penalty on the fan side with a linear benefit on the compressor side. Okay. So just a brief input on that. That's all I have on that.
Okay, thank you both. Let's put up the next question. What happens if the condenser water temperature goes below set point?
Okay, well, condensing water is going to be on your cooling towers, right? So kind of getting into that same conversation, you want to modulate the fans to maintain that set point. So realistically, you don't want to go below what the manufacturer says. That will come down, in most cases, their answer will be it's a lift requirement on the compressor. So like I had kind of briefly mentioned, a York chiller, let's say it's an 8-degree differential. So that kind of assumes worst case scenario. So think about it in the sense that you're able to achieve the coldest condensing water temperatures under usually the lowest outside air temperatures, right? And that also then corresponds to your warmest chilled water because you've got least amount of cooling demand in your system. So that's really where you're going to hit that point of like, okay, I need to maintain at least this differential between the two. So if we run with the 8-degree example, if you're able to reset up to 50 degrees on the chilled water side, you really shouldn't go below 58 on your condensing water side. If you're doing that, you either need to do one of two things: is shut your fans off basically and let that condensing water warm up, or start decreasing your chilled water temperature. Either one will work. Decreasing that chilled water temperature obviously is more expensive. That puts the energy back on the compressor and the chiller, whereas shutting off the tower fans is saving you energy, but that has a lag associated with it. So it really kind of depends. That's why we would kind of even say give yourself a buffer so you don't go right up to that manufacturer limit. Give yourself a couple degrees to allow for those extenuating circumstances when it is really cold outside. Maybe you're just flowing water over the towers with the fans off, and it still gets too cold. Then you kind of done all you can at that point. So then you may be forced to lower your chilled water temperature.
I'll add one more thing, just if the temperature does, I'm not sure if this is what you're asking, if the temperature does happen to go below the manufacturer's minimum, then the chiller will trip off. If you send it too cold of water, it'll turn off. I'm not sure if that's what you were asking as well.
Great. There's a couple questions in the chat that maybe I just want to touch on. Kind of relates to this. There was one that refers to trim and response to get the ideal condensing water temperature. Generally speaking, I don't think that that's the best way to go about it. I think it's as cold as you can get it is the better way to do it. The time when you start resetting based on wet bulb or something else, it just creates instability in the system. Let those fans run. I do like the preference of putting a cap on your fans until a certain temperature. So let's run through like the scenario of the 80% fan speed cap on your cooling tower fans. Let them run up to 80% to maintain that temperature. Obviously, if they're meeting the temperature, they begin to modulate. So they're capped at 80% up until, say, condensing water gets above 75 degrees. Then you can allow the cap to slowly be released up to, say, 100% over that last 10 degrees between 75 and its design point of 85. I would say that that's kind of a keep it simple strategy that is probably more effective than doing a condensing water reset using trim and response or PID. As far as arguments between trim and response and PID, it really comes down to what your controls contractor, what your engineer is most familiar with as far as their sequencing and their programming abilities. I think those are probably, it's a preference type of thing.
Okay. I think we do have another question lined up. How are you calculating kilowatts per ton? Did I do that wrong?
No, this is fine. It's a great one because it's kind of the holy grail. Getting an accurate kW per ton is actually harder than you think. Typically systems will be installed with a BTU meter that will give you a flow, and then you have temperatures, and you'll measure your delta T, get your flow. There's your tonnage. The problem with that is that your flow meters maybe don't stay accurate. Your temperature sensors don't stay accurate. They deviate over time. They lose contact with the pipe, or they get gunked up on. Particularly like condensing water system flow meters don't stay accurate very long. I'll just say that. I'll leave it at that. But in our case, we actually use a system called Climate Check, and it uses the refrigerant cycle itself as a proxy to a Carnot cycle. So we actually are back calculating out from a system efficiency from an ideal system to what the chiller's performance is actually doing. So we're measuring system pressures, temperatures, and real-time kW, comparing that to an ideal Carnot cycle, getting a COP based on that, and then backing out the kW per ton from that. So we're actually getting the kW per ton, and then the tonnage is calculated using the power. So that's actually a little bit different way to do it. Climate check is a whole nother discussion that we can get into, but we found that that's a really good way and a longer term solution to getting an accurate kW per ton and tonnage in real time. In real time is the key there.
Okay, that's actually all of the questions that we have today, and we're actually right on time, so it's perfect. Jim, thank you. Greg, thank you so much for your time today. So on behalf of EMA and ETC Group, I just want to thank all of our attendees. You will receive a survey for this webinar, and please do us a favor and fill it out. We're constantly looking to improve our offerings. And that email will also contain the recording to today's webinar and also a link to the on-demand credit. And for those attending today, we will be distributing certificates of attendance within 1 week. So stay safe, stay healthy, and thank you, everyone.
Thank you.
Thanks for coming, everyone.